All right, it's 2 o'clock and 7 seconds, so let's get this show on the road. This is the invited virtual reality talks session, and thanks all for coming, and for all of you out in the virtual land who I can't see. So I'm David Laidlaw from Brown University. I will be moderating things today, and I think we'll jump to our very first speaker, who is remote, as all of our speakers will be. The first talk is on breaking plausibility without breaking presence, evidence for the multi-layer nature of plausibility. And there'll be two speakers, Franziska Westermeier and Larissa Brühlbach. Both are PhD students at Uni Würzburg.
Hello everyone, and thank you for joining our talk about breaking plausibility without breaking presence, evidence for the multi-layer nature of plausibility. We are Franziska Westermeier and my colleague Larissa Brühlbach. XR has a lot of potential to impact our everyday lives beneficially, for example, enhancing learning applications, relieving from pain, or reducing stereotyping. There's a lot of research that investigates the underlying parameters. One of the most prominent is presence. Following Slater and Skabes, presence results from the orthogonal factors place illusion, social presence illusion, and plausibility illusion. The plausibility illusion is the credibility of events in comparison with what would be expected in reality in similar circumstances. There are also new approaches that do not focus on presence but plausibility, even more rigorous. Latuschek and Wienrich, for instance, postulate that plausibility results from processing and evaluation of any information from the sensory, perceptual, and cognitive layer. So we can say that the information is processed either bottom-up or top-down. You can see these different layers of information processing on the left part of the model in the manipulation space. A condition of plausibility is then generated by this processing, as you can see in the middle part. This condition of plausibility has the potential to influence qualia such as presence on the right side. But how can this plausibility be operationalized? Hofer et al. Introduced breaks in plausibility in analogy to breaks in presence. They broke plausibility by manipulating the size or physics of objects. This is where we follow up. We manipulate the gravity of objects to break the plausibility from the bottom up in the perceptual layer, since gravity is a strong prior. On the other hand, we introduce a narrative framing as a top-down manipulation in the cognition layer. Now the question arises, is a cognitive manipulation as strong as a perceptual one to counteract a break in plausibility? With this question in mind, we designed an experiment where the narrative framing was in line with the gravity-defying objects, with the idea to counteract the break in plausibility. Participants read a story about a spaceship beforehand, and they were exposed to this spaceship environment. We also used control conditions with the container ship narrative and the gravity-adhering objects.
We had 3 research questions that we wanted to answer with the 2 experiments. The first one is, does manipulating the object behavior affect the sense of plausibility? We first had to find a way to measure plausibility to answer this question. Therefore, we came up with a set of 12 questions that aim to measure plausibility. Looking at the results of these questions between the gravity and non-gravity condition, we can see that the manipulated gravity did cause a break in plausibility. The plausibility scores were significantly higher in the gravity condition than the non-gravity one. As a result, we can say that the perceptual manipulation did impact plausibility. Secondly, we asked if manipulating the top-down layer can counteract the breaks in plausibility engendered by the perceptual manipulation. In both experiments, we can see that the narrative framing did not affect the plausibility scores. This was regardless of whether the framing matched the object behavior or not. However, the differences were less extreme in the second experiment, where the narrative framing was textual and included visual elements and a more engaging story. From this, we conclude that the top-down narrative framing on the cognitive layer was not strong enough to counteract bottom-up breaks in plausibility on the perceptual layer. Lastly, we wanted to know if the breaks in plausibility affect presence. In the first experiment, we found significant effects on the subscale's involvement and experienced realism. Participants felt more present in the non-gravity condition or when they received framing. However, this might be due to the amount of interaction time in the non-gravity condition or the engaging nature of the narrative. We controlled for these factors in the second experiment and could not find any significant effects in the presence scores. So for our experiment, we can say that the presence scores were not affected by these specific manipulations. Coming back to the newly proposed model of Latoschik and Wienrich, we can say that it has the right direction of causality. The transition from the manipulation space to the qualia space seemed to work. The influences on in the manipulation space caused significant results in the plausibility scores. Also, different manipulations on the free layers in the manipulation space cause different effect in the condition space. However, we can see from research question 2, the cognitive layer needs further investigation and strengthening. In conclusion, the new model is a good basis to identify underlying factors responsible for a good XR experience, and moreover, how to manipulate and design these factors systematically. This understanding ensures that we can design better XR experiences and make our users happy. The result of our 2 studies look promising to substantiate a better understanding of the XR experience and provide a good starting point for further research of this theoretical model, its internal relations, and its advantages over existing presence models. With this, we would like to thank you for your time and interest. If you have any questions, please reach out to us.
Well, there's no question yet in the Slido, so if you have one, please log into it and ask them. My first question is, are you there? It looks like I see at least one person. I think both Franziska and Larissa were supposed to be there, maybe? Yes? So my question is, as a person here at the Viz conference, what kinds of changes do you think this suggests for XR of scientists trying to do sort of visualization science in an XR setting? Do you feel like there's any ways that it will change their experience?
Hi, first of all. I think it could have changes on maybe. So in the past, it was always these VR experiences strived for a high level of realism, but we are also examining if this realism is really necessary or if it's rather something different, like plausibility, like an internal relation. So if I have an unrealistic environment, do I still feel that I'm inside there and engaging there? So this might have an influence on that.
I feel like in scientific visualization applications, we mostly have things floating in space with no gravity. So do you think that makes it a less compelling experience for users, or is that like appropriate under those circumstances?
Hello. We think that it might be appropriate if it makes sense within the frame that you're trying to build. So as Franziska said, maybe the context is more important than it actually being realistic in our outside world. So I think as long as your floating objects make sense within the narrative you're trying to tell, it might actually be more compelling because you create an internal plausibility, even though it doesn't make sense in the real world. Whereas with the old concepts we had, we thought, oh, this doesn't make sense whatsoever because people always know that they're in a simulation. And we think that might not be the case.
Got it. One other question I had is, what kind of open questions do you feel like your work suggests for the future? What do you think people should be looking into next?
So as we said, this is just a very first empirical evidence for this new model. So a lot of more empirical work is needed to prove that this model actually has the advantages we think it might have. And also the questions for plausibility that we used are not evaluated properly so far. So they seem to work quite well, but we're mostly working on trying to figure out whether these questions are valid or not, which is one of the biggest challenges when evaluating a new model, is that you need to find a way to measure the concepts you think are important. And so far, we don't have a good standardized measurement for plausibility. And once we have that, we can look at further into whether the internal relations of this model work and also how well they translate into other XR spaces. Like we only looked at virtual reality, but of course, the spectrum is much broader than that.
Great. Well, thank you very much. Very nice work. So,
thank you.
I guess I could ask, does anybody in the room have a question that they didn't put into the Slido? I'm happy to have questions asked here too. So we'll move on to the next speaker then. The next presentation is combining real-world constraints on user behavior with deep neural networks for virtual reality biometrics. And Sean Banerjee will be presenting it. He's an associate professor in computer science at Clarkson University. And I think we'll jump to the presentation for him.
Hi, I'm Robert, and I'm here to present combining real-world constraints on user behavior with deep neural networks for virtual reality biometrics. Now, biometrics generally look at authenticating users based on some characteristic, and this can be something physical, like your iris, or more behavioral, like how you're performing a task. And as VR becomes more widespread, it's important to be able to secure the personal data that's being generated and viewed on these devices. And traditional credentials, like passwords, can be used in VR, but they have the downside of a system staying compromised until it's known that malicious users are in the system, and passwords can then be updated. And biometrics can help prevent this by acting as a second factor. And an area of biometrics which has seen a lot of work in VR is behavioral biometrics. And this is partially due to other methods like fingerprint or iris matching not being widely available on headsets. Some initial approaches to perform behavioral authentication looked at using the positional data of the devices in a nearest neighbor comparison, and also using a random forest algorithm on the device poses. But more recently, things have been shifting towards deep learning-based approaches. And one challenge when using deep learning is that the datasets are generally small. The largest has 511 users, but it has only one session's worth of data for each user. And additionally, the task is fairly inert, where users are watching a 360-degree video, so they're not moving about and really interacting. And then the next largest dataset has 41 users in it. So to deal with the sparseness of these datasets, we can preprocess our data before sending it to the network. And what Mathis et al. Did was they used a sliding window to get slices of their data, but this doesn't normalize the data. Miller et al. Used a device-level normalization, but if you look at figure 2, you can see that this erases the relationship between the devices. Liebers et al. Had an interactive phase, which allowed them to normalize to a standard height and arm length, but this requires users to do that interactive phase. So we can preprocess our data in different ways and try to come up with a general way to get around all the downsides. So the first thing we can think about is feeding the network the data as it's been recorded. And looking at this plot, this might not seem like such a bad idea. The user's motions look pretty consistent, but this is from one session. So when the user comes back on another day, their data is going to be offset based on where they're standing, and the network's going to have to learn to account for that. And we can just try and get around this by centering the data ourselves. Now it's all centered about the origin, but you can see that there's some vertical spread that's been introduced because the bounds on individual interactions have some variation. And this step and the previous one also don't distribute the data nicely in space. So we can look to account for this by using system-level normalization. And here you can see that the vertical spread is gone and the plot looks a bit better distributed. And it's most noticeable in the right-hand controller plot, which is squished a bit to spread it out in space. But one issue with this is that the relative positional changes of the devices are not being addressed. So we can look to address this by performing a per-device normalization. And now each device sort of fills up the entire space and is centered around the origin, but it's also pretty easy to see that this erases the relationship between the devices. So our work looks to recover the device relationships and use them in addition to device normalization. And we're using this using displacement vectors. And here you can see one going from the left-hand controller to the right-hand controller as that thick light blue line, the headset to the right hand as the red line, and the headset to the left-hand controller as the green line. And what this does is it encodes the relationship between the devices at every time step, and then we can add it on as a feature to the individual device normalization to recover what we've lost. So the data set we're using consists of 41 users picking up and throwing a ball at a target 10 times in a row. And we have 6 sessions worth of data across 3 different VR systems. And to perform authentication, we're using 2 network architectures. The first is based on our prior work, and this takes 2 inputs and sends them through the network, and our match value is based on the Euclidean distance of the network outputs. During testing, we adopt a query library system where we have 2 sessions worth of data. We label one the query session and the other the library session. And then we sample individual queries to compare against the entire library. The next architecture is based on Mathis et al.'s work, and it's a classifier. So we feed one input through a backbone and into a dense layer to get a class label. So as an overview of our results, we have a series of histograms where each bin corresponds with a pre-processing step, and the value of each bin is the number of times that step performed to the best for a given system combination. The Siamese network histograms are broken up into 5 groups and 10 groups, and those correspond with the number of groups we broke our 41 users into. And for training the network, we built pairs from all but one of the groups, and then we tested using that left out group. The dash test means that the query and library were sampled just from the left out group, and the dash all means the query still came from just the left out group, but now the library consists of all users. The classifier, we also have the same 5 groups and 10 groups, and for this we trained a classifier for each individual group. And we also have 1 group which corresponds with a 41 class classifier. And looking at the histogram, we can see that the device normalized with distance vectors is most occurrent, and then the system normalization is the next most. And one thing we can see that is maybe a bit surprising is that no pre-processing occurs a couple times for the Siamese network, but not at all for the classifier. And this is due to the training data on the Siamese network coming from pairs across the sessions, and the classifier being trained on one session and tested on another. But we also have that the system centering does not occur for either of them, and that tries to erase the day-to-day movements. So it could be the case that with enough data, the Siamese networks would tend towards the normalized approach over the no pre-processing. So for future work, an area of importance would be large-scale data collection, particularly looking at a lot of different VR environments, as well as long-form multi-step activities. We should also investigate how long-term sessions and comfort affect usage. Maybe it's the case that users become harder to authenticate if they find the interactions uncomfortable because they're modifying their behavior. And maybe users become more uncomfortable the longer a VR session is. Thank you.
Oh, good. And we see a person there. Hello and welcome. No questions in the Slido. Please get your Slidos going and ask questions. I'll bring up in sort of my standard question in this session. We're here at the Visualization Conference, and I'm a person who works in virtual reality and has scientists come in and look at their data and try and understand what's going on there. And I'm sort of thinking, okay, so if we wanted to deploy this there, would we have them pick up virtual balls and throw them 10 times to make sure that they were the person they said they were before we let them continue looking at their data? Or how do you see this being deployed in this kind of a context?
Sure. So the way I see this, and right now we're actually going beyond the ball throwing. We pick ball throwing because it's such a native task for any average human being. We've all thrown a ball, thrown something at a wall as a kid, and it's not a very hard task for us to learn in the VR space. So
it's also a lot easier than taking your mask off or your headset off and pressing your finger on a fingerprint reader. So for sure, that's easier.
So it's the idea here is that if you're looking at data visualization, as you're interacting in that VR space, day to day, you'd be doing this particular activity, whether it's, you're opening up your application, there's a particular data stream you're looking at. You might come in, there might be a pre-phase where you're asked, just go through your typical everyday activity. That becomes your training set. And then over time, we learn from your behavior, day to day, week to week, year to year. How does your behavior change? So the idea here is, whatever VR application we're going to be building, it has to be secured. And expecting someone to do a fingerprint, kind of unreasonable because our VR headsets don't come with fingerprint. I'm expecting someone to use a password. Well, I could tell each one of you my password. You can get into any one of my systems. And we see this, if you folks are college professor, if you're students, if you're taking online exam or, visualizing something because you've got to report it to someone else, you might give the task to your friend just because you don't want to do the job yourself. So trying to take everyday behavior in VR and making that the signature of the person. So that's sort of the goal we've been, pushing for, going towards.
So you see it being transparent. It would just sort of say, oh, you're not the person I think you are. We're gonna stop right now, kind of, without any sort of pre-calibration or, I mean, maybe the first day you'd come in and like with an iPhone, you'd rub your finger over it a bunch of times or do something. And then after that, it would just tell it with you.
Exactly. That's the sort of the ultimate goal.
And what do you think the accuracy of that is going to be like, say, compared to, say, iPhone's face recognition, which, I don't think I've ever seen it do a false positive, but not many people have tried that on my phone. It definitely has false negatives because I go to do stuff and it doesn't work.
Yep. So, one of our papers that is currently under review is actually looking at Face ID where you're masked by the VR headset. And it kind of becomes a bit challenging. It's not going to be an end-all be-all solution. I'm not the advocate that says behavior is the gold standard. No, it's going to have to be this multi-factor system where it might be where you sit down, your face is recognized, your face is obscured. It says, okay, I'm about 60% certain that this is David. Now we start your behavior and it goes a bit higher. Over time, it says, okay, I'm getting a bit more assurance. And we want to keep that temporal space low because you don't want it to be where, suppose you were visualizing medical records and this was a new cancer drug that came out. And, you've got someone in your organization that's like, I just want to release this ahead of time to all our competitors because I'm just that mean, horrible person. You want to be able to tell that person did it quickly without, it being the end of the day and you're suddenly like, well, there was a data leak.
Yeah, or I'm imagining someone at a national labs looking at simulation results of atomic explosions, and I want them to be the person that they should be looking at those. So great, thank you very much for your excellent work and presentation.
Thank you.
Okay, so our next speaker will be presenting on real-time gaze tracking with event-driven eye segmentation. The speaker is Yu Feng. He's a PhD student from the University of Rochester. And he is actively searching for an academic position in mainland China, if anybody happens to have one.
AR/VR glasses could be next generation of wearable for everyone, and people can wear it all day long. However, the challenge here is the limited compute budget to support all applications. A typical vision pipeline in AR/VR will first use optics to capture the scene. Then the image sensor will convert photons to digital signals. Digital signals will then be processed by a series of digital processors before presenting on the user's display. During this process, a majority of energy is consumed by transmitting data from the image sensor to the digital processor via MIPI-CSI interface. As we can see, 1 byte of data is order of magnitude higher than 1 byte of compute. To solve this issue, recent study proposed to move computation inside the image sensor so that we can send less data to a digital processor. However, there are still some challenges. For instance, the image sensors are usually less powerful and computationally inefficient. Therefore, the ideal algorithm for in-sensor computing needs to perform a trivial amount of computation inside the sensor and drastically reduce the data transfer between the image sensor and digital processor. Another benefit from such algorithm design is that it can also reduce the overall computation as well. In this work, we apply this idea to gaze tracking. First, let me introduce the overall gaze tracking pipeline. The algorithm will take grayscale image and feed into eye segmentation stage. The eye segmentation stage will classify each pixel into one of 4 classes. Then the segmentation result will be used in the gaze estimation stage to predict the gaze direction. The state-of-the-art pipelines typically use DM-based algorithms in eye segmentation stage. Those DM-based algorithms take more than 85% of total execution time. So in this work, we focus on leveraging ROI in near-eye imaging to accelerate the eye segmentation stage. How to find ROI is inspired by event camera. Conventionally, a frame-based camera will capture an object frame by frame at a fixed time frequency. On the other hand, when an event camera captures the same object on the left, it will generate a sequence of events instead of images. That is because only the pixels with large color shifts will be activated. In this case, the region around black dot will activate events. For near-eye imaging, events naturally become a sparse encoding of eye movements, since the background is most likely static. So our key insight here is that events naturally encode ROI information. With this key insight, we design our event-driven ROI prediction network. Our network has three inputs: software emulate event map, edge map, and ROI from the previous prediction. We choose to emulate events instead of using actual event camera so that no extra hardware is required to support our algorithm. Although event camera can operate at higher speeds such as 10,000 Hz, such higher speed is usually an overkill for many consumer gaze tracking applications. To leverage our ROI prediction, we propose our multi-mode switching algorithm. Our multi-mode switch module will use our ROI prediction network to predict ROIs. The ROI prediction network is very lightweight, so that we can easily execute it in sensor. In addition, the mode switch module can also select the execution path for the rest of the pipeline. In our case, we have three different paths. Both ROI-based eye segmentation and reuse can reduce the overall computation cost, and we only execute full-frame eye segmentation as a fallback option. As you can see, the mode switching algorithm exactly matches the in-sensor computing paradigm. A trivial amount of computation in sensor can largely reduce the overall computation and data communication between the sensor and backend processor. Here's an example of executing our pipeline. At time t0, our algorithm will always execute the full-frame eye segmentation to get a segmentation result, because we don't have previous information to predict ROI. At time t1, we will emulate event camera in software and generate event map from the previous and current image. This event map, along with edge map from the previous segmentation result, will be used in a mode switch network. This mode switch network will generate ROI prediction to crop the full-size image. The cropped ROI image then will be used in ROI-based eye segmentation to get a final segmentation result. At time t2, again, we will generate event map and edge map, and these two will be used in the mode switch network. At this time, because there's no event activities in the event map, the mode switch network will decide to use ROI-based extrapolation to predict the final eye segmentation result. This will further reduce the overall computation. On top of acceleration from our multi-mode switching algorithm, we further accelerate eye segmentation stage by proposing a lightweight segmentation network. Similar to other segmentation networks, we use a encoder-decoder architecture, but we use lightweight depth-wise separable convolution layers to reduce the overall compute cost and model weights. Here we show our model is order of magnitude smaller than the state-of-the-art algorithms. In our experiment, we use OpenEDS 2020 for the evaluation. In our evaluation, we have two variants. The first variant only uses ROI prediction with no reuse operation, and the second variant uses both ROI prediction and reuse operation. We compare our methods against three baselines: dense ELNet, deep VLG, and RATNet. Here's our evaluation on the overall gaze error. The x-axis showed normalized speed and y-axis showed overall angular error. Now let's see the result. As we can see, our newly proposed eye segmentation can achieve 2 times speed up with similar accuracy as other state-of-the-art algorithms. By combining ROI prediction and reuse, our methods can achieve up to 5.4 times speed up and retain error rate within 1 degree. Similar results can be seen in eye segmentation evaluation. Our method can keep high mean IOU accuracy with much higher speed up. Although there's a noticeable accuracy drop, the accuracy drop from eye segmentation will not affect the final gaze prediction accuracy. In addition, we also designed a first principle model to estimate energy reduction from our algorithm. Here we show the normalized energy compared to baseline. We designed 3 different scenarios. In each scenario, the sensor and backend processor will have different technology node combinations. As we can see, when sensor technology node doesn't lag behind by too much, in-sensor computing can save energy. Otherwise, in-sensor computing will introduce more energy consumption due to less advanced technology node. In conclusion, we propose a novel ROI prediction algorithm that emulates an event camera to accelerate downstream tasks. We also find out combining event camera with feedback cues from previous results can further improve the robustness of ROI prediction. This would be the first step to emulate event camera and accelerate AR applications. We are hoping this idea can benefit other visual tasks and make all-day VR become a reality. Thanks for watching.
Hello, welcome. Thanks for your presentation. Nothing in the video. May I encourage people to consider asking questions there. One question I had was, I noticed in your results example that the specular highlights appear. I'm no expert in eye tracking, but I've talked to a salesman once, how the specular highlights were very important. Any thoughts?
Hello, Dave. Your voice was cut in and out.
Am I turning my head too far?
I wasn't able to see, to hear the whole sentence. Sorry about that.
This better? Okay, yep, sorry. Did you hear my question, Yufeng?
No, I haven't.
Okay.
I haven't heard the whole sentence.
Sorry. My question was about specular highlights in the images. So I've heard that they are important for getting accurate eye tracking, but it looked like your segmentation got rid of them. They didn't show up in the results that you showed. Do you have any thoughts on that?
So we haven't looked into the high sensitive spectrum of those things. So eye segmentation is a intermediate representation in order to get a high for the input for the to model the eyeball. So I haven't looked into the direction that you asked. Yeah.
The accuracy looks good in the graphs you showed, so maybe it's not important, but I was just curious about that. One other question that I had was, you mentioned all-day VR. That sounds wonderful. What other ingredients would be necessary to add on to what you've got to go to a light, I guess you would imagine a lighter weight, lower battery life kind of thing? How much more do we have? How long are we going to wait for that?
Yeah, that's a good question. I think right now, in terms of technology, it's very hard for us to design a VR glasses or AR glasses and just wear it all day long, because the battery constraints and also the power constraints. You don't want to you want sort of like basic functionality of the AR and VR glasses, but even for that, you still need to consume way much more power and energy, and the current like form factor are not supposed to support that. Yeah, and so that's the reason we are looking into the in-sensor computing, because you don't have to transmit data to a different processing node in order to compute, or you transmit data through Wi-Fi to the sort of like edge device in order to compute and get some results. Yeah, so that's one direction. And also during my research with other like Facebook Reality Lab, they also look into some other part of the sensor. They call sparse sensing. So using sparse sensing can also largely reduce the sensing energy consumption. So that could be also some ways to reduce to make the battery life longer. Yeah.
Great. Well, thank you very much. Okay, moving on to our next presenter. The title of the next paper is Mood-Driven Colorization of Virtual Indoor Scenes, and the presenter will be Michael Sola.
Hello, my name is Michael Sola, and I will be presenting Mood-Driven Colorization of Virtual Indoor Scenes for you today. This work was done by Haikun Huang, Mark Pomplon, Jiashun Shang, Xiangfeng Lapfayu, and myself. Virtual reality enables a highly immersive experience for digital storytelling, movies, and gaming applications. One problem for artists and designers is making sure that a particular mood is experienced by users who view their scenes. For this reason, we propose a system for automatically changing the textures and colors for objects within a virtual indoor scene so that the combined effect matches a specific mood. Okay, so what problems are we trying to tackle with our approach? Virtual scene creation can be time-consuming and challenging. Automation may weaken a designer's freedom. We seek an approach allowing designers to exploit automation while not significantly altering their creative visions. How do we achieve this? Well, in the following figure, we can see an overview of the approach. Given a virtual indoor scene and a mood, our optimization process produces an output that matches the input mood. Our cost formulation is as follows, where CM is a mood cost and CR is a realness cost. WM and WR are the selected weights for each cost depending on the preferences of the user. We define the mood cost as follows, where N refers to the number of pictures used, CI in the range 0 to 1 is the cost of an image I of the scene. We define the cost of an image I as follows, where M0 is the cost of the desired mood, and MK encodes the cost of the moods that are different from the desired mood. W0 and WK are the weights of the moods accordingly. For our realism cost, we implemented the color comparison method based on the IEEE 2000 algorithm, since it provides a distance metric that accounts for human perceptibility of color differences. For more details on our formulation, please refer to our paper. For the optimization process, we use an MCMC technique, i.e., simulated annealing with a Metropolis Hastings state searching step. We start with a scene with no colors assigned, and we select a number of objects based on the current cost of the colors in the scene. Using a total of 25,000 images, we trained a deep learning classifier for the corresponding moods. In particular, each mood relates to 5,000 images. All images were from real-world indoor scenes. Images are taken to capture the outlook of the current scene, based on which the current mood cost is calculated using our CNN classifier. A realness cost is also computed to determine how realistic the textures are. Our approach modifies the input scene by optimizing it with respect to the total cost function. To effectively sample all solutions from the search space, we define a Boltzmann-like objective function where we accept the current state of the iteration with a probability comparing it to the previous accepted state. Here we can see our approach in action. During each iteration, a set of objects is selected and the colors are altered. The optimization in total takes approximately 15 minutes. The contribution of different objects to the total realism cost can be altered by the user. The same is true for the weights of the realism and mood costs. Let's look at some results produced by our approach. Here we can see results optimized for different scenes for each mood tested. The moods and scenes are, in clockwise order beginning from the top left, cheerful dining room, melancholy living room, scary bedroom, romantic living room, and peaceful bathroom. Here in the top row, we can see two results from setting our mood weight to 0 and realness weight to 1. In other words, here we are optimizing for a realistic environment. In the bottom row, we can observe optimization results for all the moods for one scene, in this case, the bedroom scene. While we focus on indoor environments, our approach could potentially also be used in a virtual outdoor scene. Further results can be seen in our paper and additional materials. Moving on, I will discuss how participants of our user studies described our results. During this research, we conducted 4 user studies. All participants were granted a monetary compensation for their participation. User Study 1, Scoring and Classifying Synthesized Results. We asked users to rate our results based on if they matched the mood optimized for. We also asked users to match a mood to an optimized scene. Users also rated 2 scenes based on how realistic they found the results, using a 5-point Likert scale. User Study 2, Comparing Synthesized Results to Artists' Designs. We conducted an Amazon MTurk study, asking people to select from artist-generated results and results from our optimization process based on how convincing they found them. User Study 3, Virtual Reality and Desktop Comparison. We had users experience our results through a virtual reality headset, as well as with a desktop application, and asked them which experience was better based on ratings. User Study 4, Ablation Comparison. Users were asked to evaluate how likely they thought that the color schemes experienced in our scene were to match indoor environments. Scenes were optimized with 3 weight configurations. Following, you can see the virtual scenes that were used for this user study. We will discuss the most important findings from these studies. For complete results, please refer both to our paper and additional document. User Study 1, Scoring and Classifying Synthesized Results. The average rating to synthesized results was 3.9 out of 5. For the voting tasks, users voted for the result optimized for in all cases except the scene optimized for scary. We contribute this to the similarity between scary and melancholy moods, which could produce some semantic issues with differences in perception. User Study 2, Comparing Synthesized Results to Artist Designs. In conducting this user study, we hope that our synthesized results were at least up to par to those handcrafted by 3D artists. Since our synthesized results received more votes or a difference of only 1 vote from artist results in 11 out of 20 comparisons, we could conclude that our approach produces similarly convincing results in our study. User Study 3, Virtual Reality and Desktop Comparison. For this study, we found that users voted for the VR experience more highly with a rating of 4.17 versus a rating of 2.81 for the desktop application. User Study 4, the Ablation Comparison. We found that users voted the results to match real-world examples in 10 out of 14 scenes. The only scenes where this did not occur were 4 out of 5 scenes where the optimization was done for mood only. With these results, we have evidence that a realistic cost helps preserve reasonable color patterns found in real indoor environments. We also conducted additional statistical analysis to find out the reliability of our hypotheses throughout the user studies. For more information, please refer to our paper. So, to summarize our main findings, proposing a novel approach to automatic adjustment of the colors of textures for objects in a virtual indoor scene, enabling the scene to match a target mood. A mood classifier trained on a dataset consisting of 25,000 images for 5 different moods. Conducting a user study based on statistical analysis for validating the approach's efficacy. In other words, if the target mood can be identified by users and enhanced in the scene's experience with a VR headset. Thank you for your time and attention.
Hey, Michael. Thanks for coming in.
Hi,
Thanks for presenting.
everyone.
I feel like it's weird. You're back there, but when I look at you there, then I realize you're looking at the back of my head. To you audience members, I don't know if I've mentioned Slido yet, but it's out there and you can ask questions. Well, nobody has yet. So feel encouraged once again. One of the things I noticed, Michael, in one of your examples was a romantic living room. And I noticed that it was like really garish magenta. And I didn't think it looked romantic. And yet your users all rated it, 30 of them rated it as romantic and 5 rated it as other. Do you have any thoughts on like what's going on there? It's a very picky question, sorry.
No, I mean, I think a part of it is one of the difficulties of the study is the subjective definition of what a mood is. I mean, I think a lot of people maybe associated the color pink with or magenta with it being romantic, but further than that, I think we could do more work with altering textures and do a further study based on that.
I guess also you only had 5 moods, I think, right? So if you had to choose between scary and romantic, maybe magenta comes up as romantic in comparison. It might be a factor of, you know, the complexity of mood might go beyond those 5 choices potentially.
Yeah, yes. That's
one other question that I have been asking everybody is, how would you see this sort of feeding into a scientific visualization application, scientists looking at some simulation data? Do you see that being, how would you fit it in?
So for visualizing scientific data, I think it could be used in experiments to collect data on how people react to different scenes. For example, using EEG device to see if there's a more objective way to see how people respond to the moods, for example, or if for automation of data sets, say 3D assets, using collections of different 3D scenes. I do believe there is a lot of further work to be done. We focus mainly on color, so there's lighting, there's all sorts of other factors that could be considered. But I think using these sort of automation processes, especially considering something subjective like mood, could be a first step to creating sort of these 3D data sets that can then be further used to study participants' reactions.
All right, great, thank you.
Thank you very much.
Okay, our next presentation is omnidirectional galvanic vestibular stimulation in virtual reality. And the speaker will be Colin Groth, a PhD student at TU Braunschweig.
Hi, I'm Colin, and I'd like to welcome you here at the Institute of Computer Graphics in Braunschweig, Germany. Today, we like to concentrate on our research on motion perception and cyber sickness prevention. We used a very promising approach for actively preventing cyber sickness, and that is called galvanic vestibular stimulation. In our work, we used this technique to create a feeling of motion while in fact not moving at all. In the last years, VR was able to win more and more support and acceptance in the society. And that makes sense. VR is almost like perceiving scenes similar to the real world. And their experience can really be fun, but only as long as your body motion also matches what you see in the VR glasses. But unfortunately, that is not always the case. If the movements do not match your body motion, this virtual experience will most likely make you sick. This mismatch between the vision and the vestibular system is called cyber sickness, and you maybe know it if you get sick on a ship or in the car. Today, a common way to fight cyber sickness is by reducing the motion in the outer region of the visual field. For example, when there's a lot of movement in the scene, you can blur or occlude the outer region of the user's field of view. With less motion in the scene, obviously also the mismatch between the vision and the vestibular system gets decreased. And as a consequence, users get less sick. However, these techniques can also reduce the presence of the user in the virtual scene. Therefore, we like to take a shortcut directly to the vestibular system and suggest a different approach here. We stimulate the vestibular system to directly create a feeling of motion that is also seen in the VR display. So in other words, we synchronize the visual and the motion perception with the movements of the VR experience. With this, we can even achieve an increased presence. We induce this sensation of motion by a technique that is called galvanic vestibular stimulation, or short just GVS. But what is GVS? GVS describes the direct and safe stimulation of the vestibular system by low electrical currents. These currents are usually applied by electrodes that are attached to the mastoids behind the ear. These electrical currents allow us to induce a feeling of motion without the body of the person moving in reality. Modern experiments with GVS only use very low currents and have often a maximum of 2.5 milliampere. Given these great opportunities of GVS, it is still an underappreciated technique in computer graphics. Most related works deal with only 2 electrodes and therefore have only one fixed axis of rotation that can be stimulated. This is of course not optimal as virtual reality content is moving in 3 dimensions. To solve the problem of moving in more dimensions, Michael Savet and colleagues proposed a new model that is called oculovestibular recoupling, or short OVR. This model uses 5 electrodes instead of the typical 2 and enables an individual stimulation of either of the axis rotations. These 3 axis rotations are called yaw, pitch, and roll. OVR is not specifically developed for virtual reality, so we start by applying this model to this environment. In our work, we base our stimulation on the OVR model and propose an extension to it to stimulate arbitrary motion patterns. In a perceptual experiment, we compare the original approach and our extension for their effectiveness. So we have 2 conditions. In the first condition, we introduce the original OVR model to VR. Here, we only stimulate the strongest rotation axis of the user's field of view. So this is only yaw, only pitch, or only roll at one point in time. In the second condition, we test our proposed extension to stimulate the exact rotation axis using interpolated currents. This is a method that is first presented here. For the interpolated currents, we address all movements that rotate around more than one axis. While OVR triggers all axes sequentially, the combination has not been considered so far. So, to put our technique in simple terms, it can be viewed as a linear combination of the OVR axis stimulations. Now, all axes can be stimulated by different electrode pairs. It is very important to choose the right pair so that the rotational components depend on each other. Please see our paper for formulas and on how to calculate the correct currents for all electrodes for a given rotation. Both GVS methods adjust the intensity based on the movements that are seen in VR. The stimulations are dynamically computed at runtime and depend on 2 things: the look direction of the user and also the movements of the video camera. All linear and angular velocities are recorded by a built-in gyroscope in the camera. In our experiment, we showed a stereoscopic 360-degree video with slow and fast camera movements. The video showed scenes of walking through a park, and that was followed by a mountain biking ride. The total playback duration was 10 minutes. As is usual for 360-degree videos, the camera movement could not be controlled by the users, but of course, they were allowed to look around freely in the video at any time. In total, we had 47 participants. Of course, in the experiments, we want to know how our participants feel. And we assess that by questionnaires as well as live feedback. We ask our participants to fill in a SSQ before and after the experiments. This is a well-known questionnaire used for cyber sickness. To know how the participants feel during the experiment, we handed them a game controller and asked them to press buttons every time that their feeling in comfort changed. Of course, this change in comfort can be related to either cyber sickness or the GVS itself. In the experiments, we used 5 electrodes. 2 were attached to the mastoids. 1 was on the forehead and 2 were in the neck. As electrical stimulation is perceived very differently between individuals, we calibrated the galvanic stimulation per person before every experiment. In this calibration step, we aimed to find the maximum current that is still tolerable by that person, and we never exceeded this maximum current in the experiment. The experiment itself was conducted by 3 counterbalance conditions that every participant went through. So 2 conditions were these active GVS sessions where we used once the original OVR approach and then our extension. The 3rd condition was the control conditions, where we attached the electrodes but did not use any stimulation at all. Between every condition, we kept a 48 hours gap to let the participants recover. The results show that 3D GVS is an effective way to mitigate cyber sickness for 360-degree videos in VR. While in the control conditions, the participants get quite sick. As soon as GVS was applied, the sickness score dropped significantly. When we take a look at the interpolated currents, this stimulation also increases the durations participants were willing to stay in the virtual environment and also make the participants feel most comfortable. For the discomfort values, identical results can be seen as for the cyber sickness scores. With the GVS applied, the comfort values increase significantly, and this is especially the case for strong movements. Furthermore, the discomfort values progress slower and also more constant when GVS is applied. And please keep in mind here that these discomfort values not only reflect cyber sickness, but they reflect all negative effects that can arise from the GVS. For example, some itching at the electrodes. Now, previous research has shown that VR can be subject to gender bias. And that is the reason why we independently investigated all results for men and women. In conclusion, we found that GVS was more effective in men to reduce cyber sickness, especially for nausea. Counterintuitively, these lower sickness scores were found after longer VR sessions, but only when the GVS was applied. At least for women, we can see that the GVS significantly reduces cyber sickness, and that can help to close the gender gap in VR perception. So let's summarize. In our work, we extended a 5-electrode GVS model to give VR users the feeling of rotational movements in arbitrary direction. With our results, we are confident that 3D GVS can significantly reduce cyber sickness and improve VR experiences. Thank you so much for watching.
Colin, that was great. Very fascinating. I feel like it sounds like magic, and like, I don't know, an IRB looking at this would say, okay, this only reduces the risks. Are there any like negative consequences that, you know, anecdotally you saw, or, you know, you say overall things were reduced. Did some people actually have an increase? Can you say a little bit about those risks?
You mean from the GVS itself?
Yes, from the simulation.
Well, so there have never been any big risks found, not from me or any other research. But what can definitely happen is things like itching on the electrodes, or if you don't do the right stimulation, for example, then of course it can even increase cyber sickness. So it can have the opposite effect, but of course we try to avoid that. Yeah, that's why we came up with these formulations. But yeah, aside from that, there's actually not that much. I mean, it always sounds creepy, like, right, to give some electrical stimulations on the head of users, but actually there's not that much side effects.
That's fascinating. We have 2 questions in the Slido. I'm so excited. Can you tell us more about the calibration? Is it possible to precisely match the signals to the perceived head position or motion, I guess?
Well, the calibration has nothing to do with that.
Well, somehow you figured out for an individual how to go from what the motion is to, to some electrode simulation. How do you do that calibration, and how close is it to reality, I guess?
Okay, so what we did is, we considered 2 variables here. So we first have the motion of the video itself, right? And then we also look, where does the user actually look at, right? Because if you look straight and the scene is rolling around you, this roll actually becomes like, let me see this. Well, it becomes
that gives you a rotation that you need to correct for, right?
Correct. And this rotation we then use with the formulas we came up with that we found from pre-experiments to correct for the actual thing that the user sees in that moment, right?
Okay, so it sounds like looking at the paper is the right way to find out the details about how
it is.
Good, okay. One other question is, what kind of additional bandwidth do you need to put into, say, a VR video so that the motion that the video is doing is reflected correctly in your stimulation?
I'm not sure if I got that question right.
If you have a video, a 3D video, it's got it could have some camera motion in it already, right? So you need to make sure that the human is getting that same motion. How much more would you have to add to the video to keep that directionality clear? Or can you derive it from what's in the video already?
I mean, correcting for the camera motion that's in the video is what we aim for, right?
Yes, so how do you know what that is?
I see what you mean. Well, so in our cases, we recorded the videos ourselves. So we had the gyroscope data for that.
Okay,
so we just used that.
A separate stream of orientation that goes along with the video.
Correct. Of the video at the recording time. But of course, nowadays you can also use optical techniques, right? Like SLAM to find out the movements.
All right.
But in our case, we just used the gyroscope data.
Great. Okay. Thanks a lot.
Thank you.
So our final presentation is comparing direct and indirect methods of audio quality evaluation in virtual reality scenes of varying complexity. And the speaker is Thomas Robotham.
Hi everyone, my name is Tom Robotham and I'm going to be presenting our IEEE journal paper comparing direct and indirect methods of audio quality evaluation in virtual reality scenes of varying complexity. So without further ado, a bit of background. Subjective audio evaluations, we use them for optimizing different algorithms based off of psychoacoustic principles. We want to make things as least computationally expensive as possible. And we also use them for setting industry standards for certain technology. Virtual reality is very multimodal, so unlike unimodal audio evaluations, we have lots of different sensors here, which can lead to multisensory integration conflicts. So we have things like when auditory information does not match visual information or auditory information doesn't match our proprioceptive cues. These can lead to conflicts which can be either detrimental or beneficial depending on what you want as your outcome. We also have a higher degree of interaction, so we can move around inside 6 degrees of freedom VR and we can interact with audiovisual objects. This leads to a high nonlinearity between subjects across testing. However, what's important to note is that the choice of method can directly influence the ability to detect significant differences across your conditions. And no standardized method yet exists which explicitly accounts for these new interactions inside 6.VR. So, a bit about the methods. So we have direct scaling. This essentially uses a scale from something like 0 to 100, and subjects will provide a value which represents the estimated magnitude of a perceived sensation or attribute. Then we have indirect scaling, which is more of a choice-based paradigm, and then we construct the scale afterwards. We want to leverage here the fact that discrimination is easier for subjects than absolute judgments. As an example, it's probably easier for you to answer if I say which of these colors is more blue than it is for you to answer how orange is this color orange on a scale from 0 to 100. In practice, we also want to make sure that things are reliable, that there's an ease of use in the method for both the subject and the test administrator, and most importantly, it fits the context of the evaluation, in this case, 6 degrees of freedom virtual reality. So with that in mind, let's go over to the test paradigm. We employ a mixed between and within subjects test design. So 4 subjective evaluation methods are used in total, 2 for direct scaling and 2 for indirect scaling. Those are MSHR, MS, EBA, and PC, and we'll come to those in a second. For each method, we employ 2 different degradation sets in 2 different sessions. These target important aspects of binaural audio reproduction for virtual reality. We essentially take head-related transfer functions and degrade their spatial resolution and then degrade their frequency resolution. For each set, we evaluate them using 5 virtual reality scenes of varying complexity. And for each of the scenes, we also ask subjects to answer a NASA task load questionnaire for such things like mental demand and effort. The methods, which I said here, these are the interfaces. So for direct scaling, we have the multiple stimulus with hidden reference. This is the reference, and there's also a hidden reference inside here. Then there's multiple stimulus, so there's just no reference and no hidden reference. Then we have indirect scaling. This is the elimination by aspects. Subjects eliminate each condition in order from worst to best. And then we have pairwise comparison, where each unique pair is presented to the subject, and the subject essentially says which one is better out of the 2 and goes through all of the different pairs. Moving on to the results. So due to time, I'm only going to talk about the results from the HRTF spatial condition, and we'll start with the direct scaling. On the y-axis, we have the scale from 0 to 100, 0 being the worst, 100 being the best. And along the x-axis, for all the results, we have the spatial condition in degrees. So 1 degree, 5 degree, 10, 20, and 30 degrees. We can see that the results show that 1 degree and 5 degree are generally considered excellent, and that the other spatial resolutions are rated worse with respect to their spatial resolution. The number of significant differences as well is reasonably consistent across the scenes, showing that subjects could rate these conditions with respect to their spatial degradation. If we compare this to the multiple stimulus method here, also a direct scaling, we can see that the results are much more compressed towards the center of the scale. This could be due to any number of scaling biases that are present, and also the number of significant differences that subjects or that the results yielded was much lower than the MSHR method. Looking at the indirect scaling, we don't have a scale similar to direct scaling, but we can construct one after the evaluation, and this is called the just objectionable difference scale, and which means we can show things on a y-axis similar to the direct scaling results. We have some nice results here for the EBA method. They show a similar, or if not more, number of significant differences than MSHR when this had a reference present. So when no reference is present, then this can still yield a good number of significant differences, or if not more, showing it's a sensitive method to the conditions present. And PC, so the pairwise comparison method, we have a much lower number of significant differences here. So this method was not as sensitive in yielding differences between the different conditions. For the NASA Task Load Index questionnaire, the results showed that EBA was less mentally demanding than MSHR. So MSHR has a reference which likely caused subjects to have more mental demand and effort when concentrating on fidelity, whereas in EBA, subjects can easily just say which one's worse and which one's best. The results from the behavior analysis show that the EBA method required the least amount of test time, This was likely due to the sequential elimination of all the conditions. So subjects can listen to all the conditions at the start and then find a movement that best excited the differences and then continue to use this movement as they eliminate the conditions one by one. There's some more discussion points inside the paper regarding the scene complexity and some comments regarding individualized versus generic HRTFs. And to end with some conclusions, the elimination by aspects method is a pragmatic and sensitive method for audio evaluations in 6.VR. It produced the highest number of significant differences. There's benefits to sequential elimination of all the conditions, such as least amount of test time and efficient use of movements. There's benefits to the parallel presentations of the conditions. The EBA requires less mental demand and effort than MSHR, and the indirect scaling approach has no scaling biases or misinterpretations with direct scaling. That concludes the presentation. Please read the journal paper to learn more about the details that I didn't have time to talk about here, and if you have any questions, I would be happy to answer them. Thanks a lot.
Well, I'm afraid that he'll be happy to answer them in email. He decided that 2 a.m. was a little rough for attending remotely, and so I think with that we will end the session. Thank you all for coming, and enjoy the rest of his.